Okay. So thanks everybody for coming. I'm very happy to introduce you to the speaker of today. His name is Chingam Fong. Sounds read correctly, pronounced correctly. And he's visiting us for the week. In fact, he's leaving tonight, but it's still available for meeting with some of you if you can. He's visiting from the University of Hong Kong, and he's a fourth-year graduate student working with Kenny G. His primary interest is an intersection of cosmic rays and solar physics. And previously, just recently finished the study on the X-ray sterile neutrino dark matter. He also received a Bachelor in Astrophysics at the University of California, Berkeley. And today he's going to tell us about the role of the coronal field in a solar gamma ray revealed by simulation. And with this, the floor is yours. Thank you.
Okay. Thank you, Federico, for the wonderful introduction and also for this opportunity to talk about my work in studying solar gamma ray with simulation. So yeah, the present work is, hi, my name is Chingam Fong, fourth-year PhD student. The present work I'm completed is with my PhD advisor, Kenny, who is also from the Chinese University of Hong Kong, Zhe, who is from Chinese Academy of Science, who did the first iteration of the simulation I'm using, and my former classmate Dylan, who's currently in Ohio, who helped with the beautiful 3D visualization, which you will see a lot in this presentation. So let's start by talking about what kind of gamma ray are we studying in this study. So the sun emits gamma ray in several sources, none of which come from the fusion itself, because fusion happens at the core of the sun, and we don't expect the gamma ray produced by fusion to escape the entire sun to the outside. So where does those gamma rays come from? They come from cosmic rays. Specifically, there are three sources of in which the cosmic ray can generate gamma ray from the sun. The first one is from hadronic particles. These are galactic cosmic rays. Energy goes all the way up to TeV and beyond. They hit the surface of the sun in the atmosphere and produce a particle shower. A bunch of secondary particles go out, and one of which is gamma ray. And the second source is from cosmic ray leptons, specifically electrons who have inverse component scattering with a photon around the sun and then produce gamma ray. And third is solar flare. During these high energy events, gamma rays can also come out. In this study, we are focusing on the hadronic components, so the ones come from cosmic ray protons. And you can also see that these three components are easily separable in observation. This is observation by Fermi Large Area Telescope, in that the hadronic components mainly focus on the 0.25 degree solar disk because they have to hit the atmosphere of the sun for the particle shower and gamma ray to come out. And the leptonic component is more of a halo around it in about 40 degree, more or less. And these two components are year-round present, but the solar flare are only isolated in certain points in time. So they are easily separable from each other. And in the present study, we are talking about the ones come from mostly protons. So how exactly does a proton turn into the cosmic ray proton turn into a gamma ray? So they come from galactic cosmic rays, so they come from 1U and beyond interstellar space, and they journey through the heliosphere and get modulated by it. And then they also have to penetrate the corona field, which is between one solar radius and a few solar radius. And then they have to go into the sun's atmosphere to interact and produce a shower and get gamma ray. Now, from the description I have before, you must realize that if there is no other component, just purely cosmic ray turning into a gamma ray, most of it will be absorbed by the sun, because the sun is optically opaque to gamma ray. If a cosmic ray just come from behind and hit the sun back here, all of the secondary particles are going to be absorbed by the center, and then we are going to observe none of it. It's only when the cosmic ray hit the edge of the sun's atmosphere that the gamma ray can escape. However, the sun does have magnetic field, and it does a few things. First of all, the magnetic field beneath the sun's surface can turn around the cosmic ray, making the gamma ray to escape the sun surface more easily. And secondly, there is a focusing effect for especially low energy GeV scale cosmic rays that they can originally not going to hit anything. They get focused around by the sun's magnetic field and then travel down there, and then they can produce gamma ray, either visible or be observed by us. So in the present study, we are just taking the galactic cosmic ray and penetrate it through corona field, and also taking into account of the PP interaction, of course, and study how much gamma ray comes out. We are going to ignore the interplanetary space heliospheric field in general. I may justify it later. And there are several interesting things about these hadronic component gamma ray from the sun. So first of all is that from the description I have above, you can estimate how much gamma ray can come out from the sun just by estimating the sun's magnetic field strength near the surface, and then calculate how much does it need to turn the cosmic ray around and be generate gamma ray observable by us. And this early 90s estimation put it around here, and only around here, because at higher energy, they estimate that it cannot produce gamma ray higher than GeV regime. Now, that has been disproven by the observation. As you can see here in this plot, I show the observation by Fermi LAT, which is in GeV to 100 GeV range. And it's much higher than this early estimated by 6 times as much. And also the spectrum is quite flat. So the cosmic rays, if the gamma ray indeed follows the cosmic ray spectrum, it will be it's shaped like this, e to the magnitude 2.7. However, this spectrum shape is quite flat in this E square flux unit. So which means in this region, we are expecting, what we are seeing is that the gamma ray conversion efficiency is getting higher as the energy gets higher, which is quite strange. And also it extends all the way to TUV regime, in this case observed by Hawk. And there's another interesting thing is that the time variation. So if the magnetic field is indeed so important in producing these gamma rays, we will expect when the magnetic field is stronger, we will see more of these gamma rays comes out. But when the sun's magnetic field is at the strongest, at solar maximum, we actually see less. As you can see here, at solar minimum, the flux is indeed higher than the entire average. And finally, there is a morphology. Unfortunately, Fermi doesn't have enough angular resolution at low energy, so this one, the plot here is only 10 GeV and above. But in the area where the Fermi does have angular resolution, what we see here is that the morphology of these gamma rays also have a lot of time variation, in that when the sun is during its minimum and low energy, it's more of a uniform distribution across the entire disk, as you can see shown by these dots and also these histogram. And when the sun is at higher energy, there's more of a equator focus at a quiet period, which is also quite strange. So now, to explain all of these, we need the complete theory have to, take into account of everything. So in this study, we are only focusing on the corona field. We build the simulation by putting a field between 1 solar radius and 2.5 solar radius and track every particle interaction in between. We track both particle produced by PP interaction and also other channels to generate gamma ray, one of which is Bremsstrahlung. And we use Monte Carlo method, just inject particle uniformly at the outside sphere. The simulation volume is between 6,000 kilometers, below the solar radius, which is the top of the photosphere, to 2.5 solar radius. And we put in some realistic sun density profile in between. Most of the interaction happens over here. I highlighted that. And we only put in corona field. And the field, we do have field inside the sun, but we assume those fields inside are exactly the same as photosphere, which is an unrealistic assumption, but I will discuss the implication a little bit. And yeah, we have cosmic ray particles only in proton between 1 GeV to 10 TeV. And we have 1 million particles per decade. Right, so about the specific corona field models we put in. In this case, we put in 2 models, and then from 2 time periods to represent active and quiet sun. The corona field models we put in are PFSS, potential field source surface, and the MHC model. The potential field source surface model is generated by this Python package, PFSS Pi. And the MHD model we downloaded from a website called MHD Web, which uses a magnetic field around the sphere calculation. And both of them uses boundary condition observed by HMI. And the PFS-pi is reportedly the less accurate of the two, but it's faster to solve. And the MHD is more precise, but it takes longer time. And also we download it specifically from this website. So we actually did not solve it ourselves. The thing we need to note here is that the PFS-pi boundary condition, we downscale it a little bit, but I think in the case we put in, we still retain most of the small scale structure in the observation. However, what we found is that the MHD model, although it's reportedly more precise, they use a boundary condition with much less resolution. As you can see here, it doesn't capture much of the small scale structure observed by HMI, which may cause a problem, but at this point, there's nothing we can do. But what we also notice is that the field geometry between two models is vastly different. This is showing the same time period, but the solution, as you can see here, in this, I show the magnetic field lines with black one represent closed field lines and purple and green represent open field lines with different polarity. They have vastly different geometry. The most important thing here is that the MHD model has more open field areas in terms of total area on the photosphere. So now we can look at some particle trajectory inside the simulation. So what I show here, first of all, look at this 3D illustration of the particle trajectory inside the corona, is that most of the low energy cosmic rays represented by blue, 1 GeV cosmic rays, they have to travel down to the solar surface, they must follow the field line. Let me explain a little bit. As you can see here, all of the blue lines, low energy cosmic rays, show this kind of gyration motion around the magnetic field. So for them to reach down to the solar surface and interact and produce cosmic ray to reach down and produce gamma ray and whatnot, they have to follow one of the open field lines. As you can see, in this case, it's mostly at the North Pole and somewhere around here. There's also an open region here. And as we go to higher and higher energy, it becomes the cosmic rays start to care less and less about the corona field, which is what we expect. And in this case, when you go from the red one, which is the highest energy at 10 TeV, they mostly just behave like straight lines and hit the sun's surface. And the yellow one is the medium energy at 100 GeV, which is somewhere in between, which is they start off straight as they go through the smaller value fields at the outside, and they start get bent around near the sun's surface as they go to stronger and stronger fields. So what that manifests on the surface of the sun is that for higher energy cosmic rays, the red ones and the yellow ones, they hit the sun's surface more isotropically. And as we go to lower energy, they start to get trapped around the open field regions, as shown over here. And this does not just show in this one model, which is showing PFSS and the active period. This shows up in all of our models of corona field. Here, I show the left side is basically the same as before, where the cosmic ray can hit, and then depending on energy and different models, PFSS, MHD, active, quiet. And in all of the cases, the low energy cosmic ray can only hit where there is a corona hole. And this, on the right side, I show where the corona holes are. So as you must realize that this means for lower energy cosmic rays to produce gamma ray, the more open field area there is, the more gamma rays that come out. So that ties back to the thing I said earlier. MHD field model has more open field area. So that is, and also if you compare between active and quiet, the quiet field, the sun during quiet field period, solved by these two models, shown to have more open field area. So what our simulation reveals is that we can sort of get the time variation we have in observation, in that when the sun is more quiet, shown by this blue line, our simulation result, if we have more flux in the low energy. And at higher energy, due to the smaller open corona field areas, the flux is lower. And also the MHD field in general has a higher flux, and that matches observation better. However, all of that is only limited to the low energy regime, somewhere below 10 or 20 GeV. As we go to higher and higher energy, the cosmic ray particles start to care less and less about the corona field, and no matter what we do, out here, nothing can get close to the observation. And I didn't show it here, but this result in this regime is more or less close to there's no magnetic field at all. Like there wouldn't be any difference. And down here, I also show right now on this sphere, I show dots represents a gamma ray emission location, not just the cosmic ray anymore, but the same pattern persists. Like the emission at lower energy, shown by the blue ones, are concentrated around open field areas. Okay, and another interesting thing is that I mentioned the cosmic ray they hit the entire surface isotropically, but that doesn't mean they emit gamma ray isotropically. And we can see here is that I'm showing the gamma ray emission locations in 2D and in 3D. Even though the cosmic ray hit the entire surface isotropically, we can still see hotspots and the high concentration areas at the sun's surface. That is to be explained. We know that the corona field is not doing anything at this point, so it must be the surface field that's being important. So that's something we need to study further, and we currently cannot say. But if you look at here, they do concentrate around the stronger field area. So it could be something to do with the field strength, but it also could be something due to the exact field geometry. Yeah, we will investigate that further. And finally, that is the next point I want to bring up is although we have shown a lot of morphology on the surface of the sun, that doesn't represent the whole story of what we observe on Earth, because we need to take into account both the location and the momentum to figure out what we observe. And to do that, we put tiny square to represent screens, observer screens around the sun, that going all the way around the sun represents observation during the entire sun's rotation. And we calculate the image we will observe in each of these locations all around the sun, and we add them up together, that being the observation during the entire 28 period of the sun's rotation. And we also divide the observation to different gamma ray energies, and also normalize it to different cosmic ray flux. And we add them up together, and finally get, then we finally get the observation, what we observe on Earth. And unfortunately, as mentioned before, Fermi only has angular resolution over here in the very high energy regime, which is where unfortunately our simulation starts to deviate from observation, and that's indeed also the case in morphology. So all of our morphology results shows a heavy focus, a ring-like feature around the edge of the sun, as mentioned before, because because cosmic rays start to care about the magnetic field less and less. And yeah, that is not the case in any of the observation during different time period and during different energy. And especially over here, where there's a focus at the center of the sun at the quiet period, we never get anything like that in our simulation. So that shows us that the corona field is not enough to explain everything in the simulation. But that's all. Simulation, it cannot explain the observation. But that's also okay, because we know that the sun doesn't just have a magnetic field in the corona, it also has subsurface field. So we do a toy model, put in a very unrealistic. Yeah, well, we artificially enhance the field below the surface by constant factor. Here I show the dotted line, which is enhancement by 25 times, and the dashed dotted line shows it's multiplied by 1,200 times, basically. And amazingly, first of all, the result below 10 GeV doesn't change by much. So that's because all of the cosmic rays, they already get turned away so much by the corona field. There's barely any change, even though we enhance the field. However, for higher energy cosmic ray and gamma rays, the result changes a lot. But we still have to be this 1,000 times multiplication to get closer to observation. And yeah, the result in morphology is also a little bit closer to observation, but that is not that is arguable, because this is depends on how you look at it. These two are not very close to each other still. And finally, I can go to the conclusion, is that we have shown that corona field is the dominant factor in the low energy gamma ray emission, in that we can use MHD model to predict both the flux and time variation in the observation. And depending on different corona field model, there's also significant difference in the gamma ray morphology, which could be a potential test for the different corona field models once we have the gamma ray morphology observation at lower energy. And finally, the subsurface field is important for the gamma ray beyond TeV regime, and we will investigate if we can put in a realistic subsurface model in our future simulation results. And for future work, we are going to investigate more time period, because right now we are only using 2 Carrington rotation, and obviously we are going to test the entire solar cycle to make sure it's not a fluke. And also we are going to, as mentioned before, have more accurate field models to see what happens over there. Yeah, that's all I can say for now, and thank you so much for your attention.
Okay, the floor is open for questions.
All right, first of all, congratulations on a very, very clear talk. Second, what's your feeling about this subsurface, whatever you call it, field, magnetic field? Do you really think it could be 1,000 times stronger than?
That's a good point. Yeah. So I didn't mention in this talk, but there are several papers already investigating effects from subsurface field. And yeah, my toy exercise, I just take whatever we observe at the top of the photosphere and multiply it by a constant factor. That is very unrealistic. And as you mentioned, yes, it is very unlikely to be 1,000 times stronger. But that's also okay, because the field doesn't need to be only different in strength. It can also be different in geometry. And the geometry is also very important. So basically, to answer your question, no, my feeling is that it doesn't have to be 1,000 times stronger, but to explain it, we also don't need it to be. It can be more turbulence, and it could be more horizontal, and there can be some other small scale structure we are not taking into account. So yeah.
That was all new to me. That was really good. Thank you. I have a question about the top figure on the right, on the top right quadrant. It's not obvious to me that that couldn't be double peaked.
Right. Yeah.
Have you done any tests using convolving your model with the Fermi resolution to see if there's any requirement for that?
Right, that's another interesting thing to point out. Yes, it is in the original observation study, they do mention this is consistent with the slight focus at the north and south pole. And
It could be a ring also.
yeah, it also could be a ring, but currently it is not, we haven't done anything to convolve our result to a Fermi resolution to see exactly how it match up, but this is definitely on the horizon what we are going to do next.
There are some predictive science MHD models that use much higher resolution for the surface magnetic field, such as during the recent eclipse. So you might try getting one of those.
Yeah, it was mentioned to me before as well, but one of the trouble is that I have to look into it, but those results, we want to test over the entire solar cycle. And we have to basically take into account every single month, the result at every single month. And basically the result we are using is currently the most accessible, but yes, definitely we can use more accurate result to for further studies.
Chingam.
Thank you.
What about active regions on the sun? You had a slide, and I don't know how many slides back from where you are here, that looked like active regions. And active regions are where magnetic fields are stronger. And so they're going to be more capable of wrapping around cosmic rays. So can you find in your distributions of the surface brightness any correlation with active regions?
Yeah, okay, so first of all, I don't think the scale I'm using so far can accurately capture the active region. So yeah, I neglected to mention the exact detail of the field we are putting in, but it's about 1 degree resolution. And we know that the observation goes way better than that. And so, yeah, no, currently we do not capture that, but also in observation, we know that the sun during quiet period at solar minimum, it produces more flux. And yeah, those times are where we expect to have less active region. But anyways, to get back to the point, we have to increase our simulation resolution and to improve it to exactly figure out how much active region correspond to gamma ray flux.
You mentioned your simulation range is between 1 to 2.5 solar radii, and then you were talking about photosphere. So, how do you cover the range between photosphere and one solar radius in the simulations?
Right. Okay. So I take the top of the photosphere as 1 solar radius, and the simulation only goes to 6,000 kilometers below 1 solar radius, and that part I think covers the photosphere, right? And most of actually that's a little bit of overkill because most of the interaction I checked happens between top of the photosphere and 1,000 kilometers below. Yeah, I think that answers your question.
So you consider the photosphere to be 6,000 kilometers below 1 solar radius?
Okay, I consider the density profile between 1 solar radius and 6,000 kilometers below. I think that part covers the photosphere. Yeah.
Thank you. One little note following up the George question. So one possible other reason, complementary to when you say that you have the flux, the solar maximum desire, is just because the solar wind structure further out, right? So it might be also another reason why you have enhanced. That's the solar modulation we see even at lower energies.
Yeah.
All right. Okay. Any more questions? Don't see any, so if not, let's thank Chingam. We'll see you next year. Thank you.
Do I need to put this back?
This one can stay up. Okay, let's do the disconnect.
Was saying now is that she was surprised by the case for.
Oh, thank you.
Did you consider just to use the data